Perfect. So take out a piece of paper. No, really, take it out. We're going to take some notes. I've already written some out, and I would like to talk through them. And I'd like you to write as I'm talking. It would be like I'm up at our old board. Fair enough? All right, cool. Now, we're talking about Coulomb's law. And last year, in our electricity unit, we actually, let's see if I can do that. There we go. Last year, you've actually seen this formula before. It's known as Coulomb's law, and it's equal to K Q1 Q2 over R squared. Now, when we have like charges, in this case I drew two positive charges here, those two positive charges are going to repel because it's a repulsive force. Now, to define the variables, the distance R is measured from center to center. The charge Q1 and Q2, that's a lowercase q that we use to represent a single charge. The force we're going to represent as an F, and it's a vector, so I'm showing the length of that force, or the length of the force gives us the magnitude. So which charge feels a greater force? That's right, they feel the same, just like two masses in a gravitational interaction. Now, if we have two charges that are different, a positive and a negative, what happens? They attract. I'm pretty sure you've known that since third grade. Now, let's get a more advanced picture than that third grade model that you have in your mind. So, a scientist by the name of Michael Faraday, which you may have studied in chemistry, we're going to spend a good deal amount of time on him later when we talk about magnetism. He tried to explain Coulomb's law by imagining something he called an electric field surrounding each point charge that extended out into space. Now, give me just a moment. Got a technical difficulty. Let's see. Now, by definition, he says that positive charges have a field that extends outwards, and a negative charge has a field that extends inwards. So we would draw those arrows out from a positive charge in towards a negative charge. We studied that last year. If we keep going, in your notes, I'd like you to define all of the variables in Coulomb's law. And I want to make sure that you get the units written down there. Coulomb's law is, again, F equals K Q1 Q2 over R squared. F stands for force, and I know you know that we measure force in newtons. What's a newton? Well, a newton is equal to a kilogram meter per second squared. Good. Now, K is a constant. It's the Coulomb's law constant. It's equal to 9 times 10 to the 9th. Units for that are Newton meter squared per Coulomb squared. That's a capital C. And that actually can be rewritten as another constant, which we'll get into again later on this year. Q1 and Q2 represent the charges involved. That's measured in coulombs. Who did they name that after? Yeah, not Faraday. Idiots. No, Coulomb. Good. And they use a capital C because it's a name. So when you have a unit that's from a name, you're going to use a capital letter. So, and lastly, R is the distance measured from center to center. That's going to be measured in meters. Okay. Now, last thing I wanted to throw out there is that if we look at Coulomb's law, maybe if I zoom in here momentarily, and let me see if I can do this. Boom. If we look at Coulomb's law, I see that KQ over R squared can actually be the definition for the electric field. So the electric field around a point charge can be rewritten as KQ over R squared. In fact, I'm going to erase that one and just look at that as around one charge. So Coulomb's law is the interaction between two charges, Q1 and Q2, and the electric field around any charge would just be KQ over R squared. If I put these two together, we get our other big formula of the day. And this one's probably the most useful, which is F equals QE. Because although it's nice to think about the force between two charges in space, a lot of times there's going to be more than two charges. And when we do that, we're going to have to sum up the electric field vectors. Yeah, it'll start to come together. I think to get a better visual of that, I'm going to let the mechanical universe take it away. I may interject a few times as if we were watching the video in class. We'll see how it goes. And after we watch this mechanical universe section, we'll get back together and talk some more. Thanks.
Anywhere in the vicinity of an electric charge, a small test charge experiences a force. If it's due to only one charge, the pattern of forces detected by the test charge is simple. The pattern's more complex for two opposite charges. Or for two charges of the same sign. And more complex still, for more complicated arrangements. But in any case, here's the point. Even if the test charge isn't there to feel it, the pattern of forces can be imagined to exist everywhere in space. This is the essence of the idea of the field. And although Faraday only imagined it, the field can also be expressed mathematically.
The force that acts on a test charge at each point in space is equal to the test charge times a quantity due only to the other charges. That quantity is the electric field.
So, that formula looks a lot scarier than it is. You do know that, right? So here's a quick screenshot of it. And let's just pull this formula apart for the electric field. So the electric field equals the sum of K, E. All that is the constant that we talked about before for Coulomb's law, 9 times 10 to the 9th, Newton meter squared per Coulomb squared. Q is the charge, R is the distance, and this R hat notation that you see at the end, this is something, it notes that it's a unit vector. It's beyond the scope of this course, but at some point in your physics career, you may see I hat, J hat, and K hat. Those translate to a vector in the X direction, Y direction, and Z direction. But for right now, don't worry about it. So if the electric field is what's that symbol right here? This one right here, this, oh, right, that's a sigma. And all it means is add them up. The sum of. It's as easy as it gets. That symbol I always found intimidating when I was young. It just means atom. Now, if that's the formula for the electric field, if I were to rewrite it in a simpler form, all it is that E equals KQ over R squared. And if we look at our formula for force, force would be the charge times the field strength. Now, why did I take a minute to do that? Because every time I've shown this video over the years, students freak out when they see this formula, as if it's really hard. It's not. It's just slightly different notation than you're used to seeing. But the key as you get smarter and older is to not freak out when you see something you don't see and you don't know, and you connect it back to something you already do. You got this.
Faraday never arrived at that definition of the electric field. But by seeing both electric and magnetic phenomena as forces in space, he managed to see further than his peers. As a result of this, and many other discoveries, he eventually became director of the research laboratory at the Royal Institution. And succeeding Davy, he became the professor there, as well as a member of the Royal Society. But it was as researcher, rather than instructor, that he saw deeper and deeper into the invisible forces of space. To Faraday, the 1/r² force between electric charges suggested that the force must be applied by something radiating outward from charges, something which, like light from the sun, never stops and never ends in space.
This is it. This diagram, this visual, explains the essence of the inverse square law. Now, we know that the universal law of gravity, developed by Newton, is an inverse square law. He knew that because of the distance of the moon and the relative force or acceleration caused by the Earth's gravitational field out where the moon was. We did that last year. You know that. Now, Coulomb's law, it turns out, is also an inverse square law. Let's see if I move my, oh, there it is. So we have the formula for gravity is gm1m2/r², where the force of electric forces, Coulomb's law, is kq1q2/r². Both of these are inverse square laws. Now, this visual, I think, really lays it out nicely. If we take this picture and let's draw a circle around it. Now, instead of a circle, let's consider that a sphere, all with a radius of 1. Now, I'm going to make a radius of 2 going around there. And can you see how the field lines that emanate out, there's going to be less and less field lines per unit area the farther away from the dot you are. Now, I could keep doing this for the next 20 minutes. Some of you would probably be psyched about that. But if we were just to take a unit of area here, we would have less number of lines through that area when we are farther away. If you can accept that, then hang out with me for a little bit longer. If the force a charge experiences is related to the field strength, and the field strength is related to the lines per unit area, I should say the lines per some unit area. So if we picture an area and we picture the lines going through it, that would be the electric field strength, would be the number of lines through that point. But let's think about the formula for a sphere. The formula for a sphere is 4πr². And I know you don't believe me because you're thinking of volume. Volume's 4/3 pi r cubed. The surface area is 4πr.
As Faraday imagined it, this something would be lines or tubes, each one capable of applying a force to any charge in its path. These lines of force would begin only on positive charges and end only on negative ones. And they would flow smoothly through space, never crossing or tangling. No matter the configuration, the charges would have a characteristic pattern of lines. The force they applied would be strong near the charges where the lines are crowded together, and weak far from the charges where the lines are farther apart. The ability to apply a force resides at each point in space, and the force arises from the intensity of lines, regardless of the location of the charges that create them. Even without such space-age graphics, this is how Faraday pictured the electric field. And it still seems the most graphic way to visualize one. But satisfying the scientific community would take another step or two. Necessarily, those steps would be mathematical.
I think you're still there. Hopefully you're still there. Still awake? It's very soothing music. Back when that video was first produced, they were really trying their best to calm students down. Now I think it just puts you in a coma. You have to admit, though, that the space-age graphics that they talk about, they do give a nice visual for field lines extending out into space. So that as we continue to do all these math problems going forward, we have some semblance of what an electric field might be envisioned as. That's it. Hope you guys are still with me. We're going to get together, I think, and do some problems right now. Stay tuned. I think. I don't really know how this is going to work out. This is like a week and a half into the future.